Hello everyone, my name is Jonathan Friedman and I'm a PhD student in Ben-Gurion University. Today's topic will be a recovery of distributed iterative solvers for linear systems using non-volatile RAM. So it is clear that HPC systems are a critical resource for scientific research and advanced industries. Therefore, we see more giant supercomputers built, and today we meet the exascale era in which supercomputers provide more than quintillion floating point operations per second. However, as these supercomputers become larger with many more components and compute nodes, they tend to experience frequent faults. And this is one of the major challenges of exascale computing. Projections indicate that the next generation exascale machines will experience failures up to several times an hour. The scientific computing world presents significant gaps between the main components of supercomputers, the computational power, main memory, and storage. As the computational power increases exponentially over time, DRAM and storage technologies stay behind. For example, it took a decade to introduce DDR5 after DDR4, and DRAM is still expensive, relatively slow, and limited in capacity. The storage is a critical resource for diagnostics and checkpoint restart, as it provides non-volatile area that can be used for fault tolerance and recoverability of applications. However, storage performances are way behind main memory performances, up to 3 orders of magnitude slower, so checkpointing entire applications frequently creates huge bottleneck to the computations. These unbearable gaps brought to the emergence of non-volatile memories and their integration in the next generation of supercomputing systems. The Aurora supercomputer, for example, is planned to consist of NVRAM. Non-volatile RAM technologies aim to feed the gap between DRAM and storage. Intel obtained Data Center Persistent Memory Module, in short DCPMM, is an emerging technology of non-volatile media. It is byte addressable like DRAM, but the data stored on the NVRAM can be retained whenever the system is shut down or loses power. In addition, DCPMM comes in vastly larger capacities than DRAM. This non-volatile memory can therefore be exploited for fault tolerance of scientific applications. As you can see on the pyramid, the NVRAM, or persistent memory, creates a new tier between the standard storage devices and the volatile memory hardware. Persistent memory aims to have memory-like performances, but there's still a certain gap. For example, obtains bandwidth on write operations is about 8% of that of DRAM. Last year, we presented in the FTXS workshop the capabilities of obtained DCPMM in 3 main use cases of memory expansion, fast storage for diagnostics, and fast storage for checkpoint restart. We considered both transparent checkpoint restart, for example, with DMTCP, and explicit checkpoint restart, for example, with the SCR library that stands for the Scalable Checkpoint Restart. Memory expansion is enabled in configuring the DCPMM in memory mode and allows executing much larger problems on a single compute node. Fast storage for diagnostics and checkpoint restart is enabled in UpDirect mode using persistent memory 5 systems, which support direct access to NVRAM. A main example of such promising file system is DAOS. While these use cases bring a complete solution for increasing performance and fault tolerance of scientific applications using NVRAM in the general case, with minimal changes to applications, in this work we focus on how the NVRAM can be used directly in specific cases of algorithm-based fault tolerance. Mathematical solvers account for 50 to 90% of scientific applications operations. Specifically, linear iterative solvers are main kernels in scientific computing, especially when direct methods are expensive or do not exist. Distributed versions of iterative solvers allow solving larger problems on several compute nodes concurrently. Trilinus is an example for a collection of reusable scientific software libraries, including linear iterative solvers. Trilinus supports the major parallel architectures, including distributed implementations with MPI. Fault-tolerant solvers in Trilinus was investigated at Sandia and are enabled by selective reliability, which makes efforts to make these solvers less sensitive to faults. This emphasizes that many efforts are made to support fault tolerance of iterative solvers, so these solvers can be executed reliably on future exascale systems. Reviewing now the main mechanisms that support fault tolerance in iterative solvers, we already mentioned checkpoint restart. Checkpoint restart is used to persist the state of the solver to a storage device every certain period. When failure occurs, this data can be retained back to the memory and computation can continue. The advantage of the checkpoint restart mechanism is that the state is read back after a failure and the solver can continue immediately without any reconstruction stages. However, frequent checkpointing, especially of the full state of the solver, is very expensive, and especially if executed with I/O calls to a standard disk. Other mechanisms take advantage of the intrinsic convergence features of iterative linear solvers. These methods do not persist large amounts of recovery data, rather they assume that the solver can naturally recover from faults and make up for the lost accuracy. However, it might require extra iterations to converge and make up for the lost calculations. As you can see in the graph, the blue and green lines represent the quality of a PCG solver result when certain faults incur. Now, let's talk about exact state reconstruction techniques. In short, ESR. ESR is an algorithm-based fault tolerance mechanism that provides exact state reconstruction of the computation after failures without the need of checkpointing the full state. Specifically, NVRAM ESR techniques create certain level of redundancy to only some state variables by keeping their copies on the RAM of other nodes. When failure occurs, even if on several nodes simultaneously, the copies can be read back from the neighbors and the other state variables are reconstructed by local calculations. Then the calculation can be continued. In this work, we found interest in the previous work of Chen that introduced an in-RAM ESR technique for linear iterative solvers. This method applies to iterative solvers that involve sparse matrix vector multiplication, in short, SPMV. This technique utilizes the transference of values between nodes as part of the SPMV operations. This naturally creates redundancy to any vector V that participates in an SPMV operation. However, to support the recovery from failure of C-simultaneous nodes, C+1 copies should be made on different nodes. This is because if C arbitrary nodes fail, we need to ensure that we still have an available redundancy for each process. Therefore, the SPMV operation is augmented to what is called a SPMV operation to create enough redundancies. In case of a failure, each failed process collects its redundancy from the other survived nodes and uses this recovery data to reconstruct the entire state of this process on a replacement node. Then the computation can be continued. The augmented SPMV operation can be applied every certain number of iterations, which means the redundancies can be shared every certain period and does not have to be created every iteration. But then, when failure occurs, we can reconstruct only from the last recovery data available. 2 years ago, Pachajob presented a generic strategy to create ESR techniques for various linear iterative solvers. He presented a state reconstruction meta-algorithm that can be applied to produce ESR algorithms for certain solvers. For example, the conjugate gradient and the biconjugate gradient stabilized methods. However, in-RAM ESR has limitations. First, the memory footprint of the recovery data increases dramatically with the number of nodes. Suppose keeping C copies of each SPMV variable when C is a portion alpha of the number of compute nodes. As the size of the problem increases with the number of nodes in weak scaling, and the number of copies increases also with the number of nodes, we get a quadratic memory overhead. And since the DRAM is an expensive resource, as we know, we need to find ways to eliminate this overhead. Moreover, the transference of all these copies between different nodes brings to dramatic time and networking overheads. And finally, as this method relies on DRAM for recoverability, and does not rely on NVRAM hardware, this is a disadvantage for the next supercomputers that will integrate NVRAM. Before we dig into our solution, let's present two main architectures that include NVRAM in HPC systems. In the homogeneous NVRAM cluster, each compute node is equipped with its own node NVRAM cards connected directly to the CPU bus. This architecture is relevant, for example, in supercomputers that integrate NVRAM on node for main memory expansion, and also relevant in cloud HPC computing when the goal is to equip each compute node with as much as compute and memory resources as possible. The second architecture holds the NVRAM on remote subcluster on dedicated nodes. We call it Persistent Recovery Data NVRAM Subcluster, or in short, PRD NVRAM Subcluster. This architecture is relevant, for example, in Aurora, when the DAO storage system is planned to consist NVRAM outside the compute nodes. So in this work, we use the NVRAM to enhance the capabilities of exact state reconstruction techniques. In the model we call in NVRAM ESR, the SPMV redundancies are persisted to NVRAM only once at each persistence iteration, instead of creating several copies and being transferred to the RAM of other nodes. As in RAM ESR, a persistent iteration can be applied every certain period. As you can see in the algorithm, it applies both in the local and remote cluster architectures. The reconstruction stage of in-NVRAM ESR depends on the cluster architecture. For the homogeneous cluster, if node fails, we need to wait until it recovers so we can access its persistent data and reconstruct the computation. In the PRD subcluster architecture, when compute node fails, we can retrieve its recovery data from the remote NVRAM that's still alive and reconstruct the computation on another spare node. To implement in NVRAM ESR, first for the homogeneous NVRAM cluster, we use the Persistent Memory Development Kit, PMDK. Specifically, we create a persistent memory object to each vector we want to persist with the libpmmobj library, and we store these objects on allocated pools on the byte-addressable NVRAM. To implement in NVRAM ESR for the remote NVRAM subcluster, we use an extension of one-sided MPI communication that enables direct access over RDMA to remote MPI windows allocated on byte-addressable NVRAM. This method is implemented with the post-start complete wait synchronization protocol by invoking an access epoch on the compute ranks and invoking an exposure epoch on the target rank. Each architecture has pros and cons. In the homogeneous NVRAM cluster, persistency is local, so there are no network overheads or surge on a subcluster. However, if a compute node fails, we need to wait for its recovery before we can continue reading back the recovery data and reconstructing the computation. In the remote NVRAM subcluster, however, we might experience networking overheads for accessing the remote subcluster. In addition, the NVRAM subcluster is a single point of failure, although this issue can be solved with RAIDing on the NVRAM nodes. Main advantage of the remote subcluster is when node fails, the computation can be reconstructed on a spare node that accesses the recovery data from the remote NVRAM. Now, let's see an example of in NVRAM ESR for the preconditioned conjugate gradient solver. According to the ESR technique, in the in-RAM ESR method, redundancies are made to the conjugate direction P, the P variable, and are sent to other compute nodes RAM during the computation. In our version of in NVRAM ESR, we persist the variable P to the NVRAM only once at each persistent iteration, locally or remotely. Now, let's talk about the results. The left graph presents for each number of processes how the RAM usage is partitioned into the computation itself and for recovery overhead. You can see that in NVRAM ESR does not incur any overhead on RAM for recoverability. Because we have only 256 processors on our system, we can simulate only that number of compute nodes, so we executed in-RAM ESR at the stress cases of alpha equals 1 and alpha equals half, which means copies are sent to all the processes or only at half of them respectively. This helps us to simulate memory overhead in extreme cases that would appear in larger systems. The right figure shows that NVRAM usage increases in linear fashion when problem size increases, as we keep only one copy in NVRAM. We now measure the time overhead for a single persistence iteration. To simulate the homogeneous cluster first, we have only one node containing NVRAM with 20 cores. We consider persisting to NVRAM via certain means: via local persistent memory file system in green line, via PMDK as described before in orange line, and via local MPI windows in pink line. We also compare these results with persisting to local SSD device, which appears in red line. Note that the vertical axis is in log scale. So the results show that writing to NVRAM with persistent memory aware file system may be more efficient than creating pools with PMDK, but still more efficient than writing to SSD. The horizontal lines present the extrapolation of this simulation to several NVRAM compute nodes. Because the persistent operation is local and is executed in embarrassingly parallel fashion, we keep the penalty constant. The in-RAM ESR time overhead, however, presented here for alpha equals 1 and 0.1 increased dramatically. To estimate the time overheads of a persistence iteration in the remote NVRAM subcluster, we simulate in NVRAM ESR at up to 256 nodes, which you can see in blue line. For reference, we consider also persisting the recovery data to a remote SSD in black line. The azure line is for reference and presents the time penalty for transferring the recovery data to remote window on RAM, which means this recovery data is not being persisted, just being transferred. It is very interesting to extrapolate these results up to 9,000 compute nodes, the number of compute nodes in Aurora. We estimate in NVRAM ESR to be much more efficient than in RAM ESR in larger systems. As we keep extrapolating the results to Aurora supercomputer, we want to remind Aurora has 9,000 compute nodes and around 10 petabytes of main memory. Aurora contains around 230 petabytes of DAO storage, including NVRAM. Extrapolating the memory overhead of in-RAM ESR, we get up to 3 petabytes overhead for alpha equals 1 and 300 terabytes for alpha equals 0.1. And this is for a computation that occupies the entire computer. In NVRAM ESR can reduce this overhead to 300 gigabytes on NVRAM, eliminating DRAM overhead for recoverability and leaving free the DRAM, what can enable executing larger problems. So, for conclusion, in this work, we investigate how NVRAM can be utilized in algorithm-based fault tolerance techniques for iterative linear solvers, leaving behind the need for standard storage devices. We show how to access directly NVRAM with direct access using the PMDK library and the one-sided communication of MPI over RDMA. In comparison to the in-RAM ESR, our solution decreases significantly the memory overhead and the time overheads for supporting the fault tolerance. We consider both on-node and remote subcluster NVRAM architectures as they are both relevant in our days. In this opportunity, we encourage scientists to examine our method on larger supercomputers and particularly on Aurora. For discussion and future work, we would like to research how we can reduce programmer efforts by automation of the ESR technique. And we also would like to extend this work to algorithm-based fault tolerance of direct solvers as well. And finally, we hope that NVRAM technologies would continue to develop by other vendors, even though Intel just announced the death of Optane. We still believe that NVRAM has great potential in closing the gaps in HPC, and we will be very happy to hear more about it. Thank you,